We now explore beta decay. When analyzing fermion generation 1 mass magnitudes, we get an exact representation of beta decay as the electron neutrino plus the electron plus the up quark equals the down quark. All the fermionic components of beta decay fit together in a very exact mathematical fashion. In the upper portion of the graphic below, we show the geometrically derived fermion generation 1 mass magnitude matrix used throughout this video. Both the top row and first column basis vectors of the matrix give a representation that is equivalent to beta decay. Notice that stated at the top of the matrix, we have electron neutrino plus electron plus up quark equals down quark, where the mass magnitude values of the first row or first columns add up accordingly. Beta decay is defined in this fashion to within 0.9997%. In the lower half of the graphic below, we diagram beta decay geometrically and denote that all right triangle legs are the geometrically derived square root of the electron's mass magnitude, with all hypotenuse the same geometrically derived square root of the electron's mass magnitude multiplied by the square root of 2. We now show another graphic with an equivalent representation of beta decay is derived from the matrix at the top of the graphic. We now make a comparison using the geometric mean versus the usual arithmetic mean. Specifically, when looking at any chart of fermion GeV² masses, it is hard not to notice that the up quark has exactly half the mass of a down quark. This is diagrammed in the lower half of the graphic below. When analyzed by arithmetic mean, the up quark times 2 equals a down quark. But when computing, utilizing the geometric mean, as in the lower right half of the graphic below, the up quark plus electron neutrino equals a down quark. This gives beta decay a definite bilateral symmetry when analyzing particle representations that are geometrically derived from their respective mass magnitudes. Next, we explore why bare mass values for the individual particles involved in beta decay do not add up when using a usual conventional fermion chart. In other words, when computing the fermionic components of beta decay with the arithmetic mean, the down quark does not equal anti-electron neutrino plus electron plus up quark. But when computing the same values, utilizing the geometric mean, the down quark is equal to the up quark plus electron neutrino, just as beta decay warrants. Next, we have pie chart presentations of the concepts covered in the last couple of slides. There is one pie chart for the arithmetic mean and one pie chart for the geometric mean. They're both representations of beta decay, which in turn, they are both representations of all fermion generation 1 particles. When analyzed by the arithmetic mean, the up quark times 2 equals the down quark. But when computing, utilizing the geometric mean of mass magnitudes, the up quark plus electron neutrino equals a down quark. This gives beta decay and fermion generation 1 itself a definite bilateral symmetry, as shown by the half circle in the lower right half of the portion of the diagram below. I ask you, why do geometrically derived representations of fermion mass magnitudes fit together in such a symmetric fashion? Are these representations arrived at by chance? We now examine the overall geometric structure of generation 1 in detail. We start with a fermion generation 1 matrix correlation. In the diagram below, we have two slightly different but exactly equivalent representations of the matrix used throughout this video. We want to observe the fact that if we divide the matrix into 4 sectors, as shown, to a very high degree of accuracy, each sector equals the GeV² bare mass of a down quark. Also, if we add every cell in the matrix together, we get a total of 4 down quarks. This symmetry is also exhibited in the next diagram, where we show that the total of all cells for the top row, or the first column of the matrix, are equivalent to the square root of 4 down quarks. Next, we view a diagram that shows that each row of the geometrically derived fermion mass matrix used throughout this video contains a total of 2 right triangles per row, one composed of the electron neutrino, electron and up vectors, and the other the down quark, represented as 3 vectors or a right triangle. For the top row or first column, all right triangle legs are the geometrically derived square root of the electron's mass magnitude, with the hypotenuse being the same, times the square root of 2. The triangles of rows 2, 3, and 4 are exact representations, but are not drawn to scale, as they would get progressively larger. We now observe an equivalent matrix that exhibits the relationships between the column vectors. These are depicted the same as the row vectors were, but now as 2 right triangles per column instead of per row. Another way of visualizing these matrix row and column concepts is to view them when composed of their geometric components only. Both halves of this diagram are equivalent representations of the same matrix used throughout this video. Consider the down quark representations in the red boxes of this diagram. The square root of the GeV² mass magnitude of the down quark would be a dot in the same dimension, where the observable GeV² mass of a down quark at GeV² would be depicted as the perimeter of a right triangle. In this diagram, we combine all former representations in this section into a full diagram of fermion generation 1. The values at the top of each cell correspond to the values in each cell of the fermion mass magnitude matrix at the top of the graphic. The main diagonal values in both representations of the graphic below would be actual fermion GeV² masses. It is handy to remember there are only 2 vectors added in different permutations that compose the entire graphic of fermion generation 1. They are either the vector, that is the geometrically derived square root of the electron, or, which is all the triangle legs in the diagram, or the same geometrically derived square root of the electron multiplied by the square root of 2 for any hypotenuse. In each cell, combinations of these 2 vectors are added together in a semi-linear fashion. To compute a cell total, we perform an addition of all the blue vectors per cell, and 1 addition for all the black vectors per cell. We then multiply the total combined blue vectors in any cell by the total combined black vectors in the same cell to achieve the product listed at the top of each cell. These values at the top of each cell are identical to its corresponding cell in the fermion mass magnitude matrix used throughout the video. Again, I'm going to ask you, the viewer, can these graphic descriptions of fermion generation 1 as derived from first principles, are they some kind of a fluke? Why do these elementary particles reveal themselves in such a comprehensive geometric fashion? Is this by chance?